Все пообедали и готовы дальше.
So we have all had lunch and now are ready to digest further information. And we are going to have a very interesting speech by Marco Slot from Citus Data, who is going to tell us about horizontal scaling in Postgres. And I believe that will be the first transparent horizontal scaling that is implemented not as a hex to core, but as a PGConf extension. And now Marco Slot will share his experience in this sphere. You're welcome.
Thank you. So I'm going to be talking about scaling out Postgres for data-intensive workloads. And in particular, I'm going to be talking about a new extension called PGShard, which is an open source extension for Postgres that we released about 2 months ago. And so at Citus Data, we deal a lot with kind of real-time data-intensive applications. So large data sets where we want to do fast queries. And typically, those types of applications require horizontal scale, where we can keep adding more machines to add more data or to keep making queries faster. And so a lot of companies actually use NoSQL solutions for those types of workloads. And particularly because, not so much because they are fast, they're not necessarily faster than relational databases, but they provide kind of seamless horizontal scaling. So it's easy to add nodes and fit more data. And so we're asking, like, what if Postgres could do that? And so at Citus Data, we have kind of a family of projects, if you will. We have CStore, which is a foreign data wrapper, which allows you to store tables in columnar format. And that means that all the data in a column is stored as one block on disk. And this has two advantages. One is that if you have a big table with lots of columns and you do queries that hit only a few of those columns, you can do much less I/O. And the other big advantage is that in a column, the data tends to be quite similar, as in it's similar data type, often similar values. And so you can actually compress it quite well. So CStore will compress the data for you, and you can fit more data on disk, more data on memory. CitusDB is kind of our core product. I'll talk about that in the next slide. It's a scalable analytics database. And our latest addition to the family is PGShard. And it is a library for transparently sharding Postgres tables across many nodes. And I'm going to talk about that more. So what is CitusDB? So CitusDB is a scalable analytics database that extends Postgres. And basically, it helps you shard your data across many what we call worker nodes. Now, these are just Postgres nodes, essentially. And what CitusDB can do is it can automatically parallelize queries across those shards. And so it will use multiple cores on each machine, and it can parallelize it across multiple machines. And now CitusDB kind of makes some modifications to Postgres, but they're very small because mostly it hooks into the planner and the executor logic of Postgres. And I'm going to actually provide an example of that because PGShard does the same thing. And because the changes to Postgres are quite small, it's easy for us to keep updating it to the latest version. So pretty soon we'll have a release where we'll support Postgres 9.4. And with all the extensions and data types that come with it. So there's a bunch of CitusDB customers, and if we ask them, like, what kind of feature would you want us to add, we'll just kind of get the same answer. It's great that I can do fast analytics with parallel queries across all these shards, but what I also want is that I can do kind of real-time data ingestion, so basically fast inserts and updates on my data, because CitusDB uses kind of bulk loading. And we've seen customers kind of build that themselves, which is a lot of work. And we also talked to just other Postgres users and running into scaling problems, basically. Some switch to NoSQL, as I already said, and others actually implement kind of application-level sharding schemes where you kind of have to manage adding nodes and removing nodes and handling failures and partitioning the data. So that's also a lot of work. And so we asked a bit more, like, what do you really want if we solve this problem of data ingestion for you? Well, particularly customers wanted to be easy to scale out a cluster, adding new machines, retiring old ones, and also if one fails, there should be a way to handle that. But most of all, it should be simple and easy to use and just work with Postgres. So not be an alternative solution, but just work essentially as a Postgres extension. And with these types of workloads, the transactional semantics tend to be less important. It's more about being able to insert quickly and a lot. So that gives us some technical challenges, such as how are we actually going to shard the data in the cluster in kind of a general way? When there's a failure in the network or a node fails, what do we do? How do we, if we have this concept of a sharded table, how do we do kind of query planning across that table? And how do we put this into Postgres? So I first want to look at all those challenges, and first I want to look at sharding. But before I tell you how PGShard does sharding, I'm going to show you like how do people traditionally do sharding. And basically, usually you find some dimension in your data. Could be user ID or it could be year in this case. And you set up a couple of databases. You put 2012 in there, 2013 in there, 2014 in there. Okay, that works. So now we have 3 databases. We can kind of query them in parallel if we implement that. But now, you know, what if these databases are getting heavily loaded and we want to scale out? So we could add a node, but now what do we do? So, well, okay, obviously it's 2015, but if we want to move load from those nodes to that node, we'll have to repartition our data or split some of the partitions in half. There's no obvious way to do this. Well, there's one obvious way, which is, well, let's just duplicate all the nodes. So let's set up replicas. So now we have, you know, spent a bit more money than we wanted to, but now we have twice as much capacity. Okay, cool. But now what happens if a node fails, right? So basically the node with the 2012 data failed, or one of them. And so now our 2012 the capacity has been cut in half. So all the queries that used to go to that node will go to the other node. So effectively, we've cut our capacity in half with just one failure. So in PGShard, we're taking a different approach, which we refer to as logical sharding. And so the idea with logical sharding is that you make your kind of sharding, your partitioning decision, independent of your physical machines. So an example. Basically, we're going to cut the data into small pieces and then kind of distribute them across the nodes. And when we do this, we can also replicate the pieces, the shards. So for example, we have a shard number 1, which is placed on node 1 and 2. And then shard number 2 is placed on node 2 and 3, and so on. And you can kind of distribute this somewhat randomly. So now let's do our exercise again. What happens if we add a node? Well, because we've just got small pieces that are more or less independent of the physical machines, we can just move them around to that node. And you know, if we add nodes, and you know, we nicely distribute the shards across all those machines, then when a machine fails, what happens? Well, okay, there used to be queries going for shard 1 to that node. They now go to node 2. Queries for shard 4 will go to node 4 and node 5. So actually, after the failure, the load will be nicely distributed over the other nodes. And actually, if we have 100 nodes, which PGShard could well support, you know, you only have a 1% increase in load on all the other surviving nodes. So that's a much more graceful way of handling failures. So all these shards require us to keep some, you know, we kind of need to keep track of all those shards. So in PGShard, we have the concept of a master node. And the master node is a Postgres database. And on it, you install the PG-shard extension. It's just a regular Postgres extension. It's very easy to install. And the master node keeps track of three things. One is distributed tables. Another is the shards that make up the distributed table, the logical shards. And the third one is placements of the shards. So where are the shards stored? And the way in which the shards are stored is actually on what we call worker nodes, which are just regular Postgres databases. No, don't even need the PG shard extension. And we put it in regular Postgres tables. We put the data in regular Postgres tables. And they'll be named something like the distributed table name, meaning the name of the table on the master, underscore, and then shard ID. So each shard has a number, as we saw on the previous slide. So that gives us more or less this architecture. There's a master node, which is Postgres, plus the PG shard extension, which has the concept of distributed tables and shards and placements. And then there is any number of worker nodes, which are just regular Postgres nodes. And the master is actually going to control them by sending queries. And I'll show you how that works. Now, one thing about this architecture is I've shown you like what happens if a worker fails. We can redistribute the load, and we've made replicas of everything. If the master fails, what can we do? Well, the master is just pretty much a regular Postgres database. The metadata it keeps are regular tables. So whatever backup or replication mechanism works for Postgres works for the master node as well. So you can use streaming replication, or you could just do PG dump and put it into another node. In the cloud, you could use back EBS volumes. Even if you completely lose the master node, it's still possible to get back the metadata from the workers, actually. So, okay, that's kind of gives you some idea of the overall architecture. Now, what does that mean to you as a user? So, well, some part is missing here. First, you go to GitHub. It's on GitHub. You do a git clone, and you do a make and a make install. And then finally, there's some configuration settings. Mostly, there's one configuration file which on the master, which contains the host names of the workers. So after you've done that, you go into PSQL, you do create extension PG shard. Only need to do that once. After that, you create a regular Postgres table, no magic yet. It's just a table, you can query it. And, well, some magic here, not that much. You call a function with, this is a UDF, so you do select and then call the function. And the parameters are the distributed table name of the table that we just created, and a partition key. And so this is one of the columns. And the partition key specifies what key we're going to partition data by into shards. But not that much happens here, actually. Some more magic happens over here. When we do a select master create worker shards with the table name, we can specify the number of logical shards that we want to chop the table into. And we can specify the replication factor of each shard. So in this case, we're going to store every shard on 2 worker nodes. Now what will happen here is that the master will connect to all the workers to essentially recreate this table, but then with the shard ID suffix, if you remember. And also any indexes that you've placed on that table will be forwarded along with it. And so after those steps, if you look at the metadata on the master, this is kind of the most interesting table. So they're in a separate schema, and you can query that table. And so in the first column of this table, you see the shard ID. So remember, that's what comes at the end of the table name on the worker. Relation ID is just the identifier of the table in Postgres. Storage can be T for table or F for foreign tables. You can use this in combination with foreign tables. And then there is a min value and a max value, and they're maybe the most interesting. They specify what's in the shard. And so these are kind of strange values, but PG shard uses hash partitioning. So when we insert a row into a PG shard table, we look at what is the value of the partition column, take a hash, that gives us some arbitrary integer, and then we look at which shard does the hash value fall into? Where does it lie between min value and max value? And so that's how PGShard implements hash partitioning. So after you set up your distributed table on the master node, you can actually start querying it. So you can do inserts, update, delete, selects. And so how does this work? Because the distributed table is not a regular Postgres table. It just doesn't go to disk. So Postgres provides this pretty unique feature, which allows you to hook into the planner and the executor logic that would normally be used. So if you look at the PGShard source code on GitHub, you'll find these lines somewhere. And the important part is the planner hook variable. So this is a variable in Postgres that an extension can set or read, and it's a function pointer, and it defines what the planner function, which planner function Postgres should use. And so PGShard replaces Postgres's planner and also the executor functions. When you do something like this, it's very useful to keep reference to the old value of the planner, because PGShard is only going to deal with distributed tables. If it sees, this is not a query for a distributed table, it's going to send it back to the regular Postgres planner and let it do what it needs to do. And so let's look at the planner logic itself. So we take the most simple case, but it's actually kind of similar for updates, deletes, and selects as well. But inserts kind of always apply to one row, the one they create. So the first thing that the planner does is it finds any clauses on the partition key. So for inserts, this is sort of a trivial step. We're inserting a row where the customer ID is HN892. But for updates or selects, there could be multiple clauses, of course. And then the planner finds the shards, where this partition key goes into. So it takes the hash of HN192 and finds the shards for which min value, or for which that value lies in between min and max value. And so that gives it a shard ID. This is like just a query on the shard table. And so the result of that is a shard number, a shard ID. And what it then does is very simple. It just takes the original query and rewrites it to include the shard ID at the end of the table name, because this is the name of the table on the worker, where this row needs to go into. After planning, the next step is execution. So an important part of the executor as a first step is actually acquiring locks for the shard. Because we do replication, we need to keep the replicas consistent. So if we do an update that sets a value to 1 and then an update that sets a value to 2, and that happens in a different order on the other replica, then we'll have inconsistent replicas, obviously. So what type of lock you need depends on the query. For select, we don't do any locking. Selects always go through. For inserts, there's a shared lock. That means we can do concurrent inserts on a table. A consequence of that is that kind of the default order of the table might be different on different workers. But since a relation is a set, that shouldn't matter too much. Now, if we do an update or a delete, the executor will require an exclusive lock, meaning there's no other update that can go through at the same time, and also no inserts. But you can actually, do concurrent updates of different shards. You just need to lock the shard that you're going to update or insert to. So once the locks are acquired, the next step is basically to start querying the workers. So for each active placement, so placement is part of the metadata, the master will get a connection from the pool, meaning sometimes there's already an open connection to the worker, otherwise it creates a new one. And then it just uses the libpq functions built into Postgres to send the query to the worker. Now, if something fails, let's say you're doing an insert and that fails, the placement will be marked as inactive. So I'll show you this in a bit more detail. So normally, when the master node gets an insert on the distributed table, it will actually itself send 2 insert queries to the 2 worker nodes, because the replication factor is 2, which store shard number 1 in this case. Now, normally this will go through fine. Sometimes it might happen that an insert fails. So now we have a slight problem because we have one replica where the insert went through and another replica where the insert failed. So what we kind of currently do is sort of optimized for availability. We hide this from the user, and the master node marks that placement as inactive in the metadata. So we won't do any more queries on it. So at this point, we kind of only have one replica or one consistent replica in the shard of the shard, and an operator can kind of recover inactive shards later on. Now, so that's kind of describes an insert. So what happens if we do a select? So we'll follow the same procedure we had before. We look for clauses on the partition key. So in this case, the customer ID. And so, I mean, this is very, PGShard is heavily optimized for cases where, you know, you're reading and writing data for a particular user or some other key. And that select query will result in a shard ID again. And so we rewrite the query to replace the table name with the table name plus the shard ID. And then we send that to the worker using libpq. Now, of course, now we're going to get back results. And so those results are kind of collected in memory and then passed back to the user, or if the results are being written to a file, written to a file. And so what happens there in case of failure? Well, normally the select goes to one of the placements. Like, we don't need to send it to both. We only need one result. Now, if that fails, then the select will just kind of fail over to the second placement. We don't need to do anything special here because we didn't make any changes. So actually, this just kind of hides the query failure from the user, because the user will still get back results from the second shard. So what happens if we do a select on multiple shard, meaning we didn't specify an equals clause on the customer ID? So here we only say, okay, we want the review date to be greater than 1st of January. Well, PGShard is kind of supports these types of queries, but does it in a very simple way. So it will pull whatever data it needs to answer this query from the workers into a temporary table on the master, and then run the query. So, like for each shard, basically, that it knows about, it'll write a select query and then send them. And it will get like a big table with only the ratings and then compute the average. The other product I described earlier, CitusDB, will compute the average in a distributed way. So it will do two things here. Basically, to compute an average in a distributed way, what it will do is it will send a sum and a count query to every shard, or to every worker for every shard. And then the master will take the sum of all the sums and the sum of all the counts and divide the sum by the count. And so that gives you the average in a distributed way. And it will actually also run all those queries in parallel. And also, if a node contains multiple shards, it can use multiple cores. So what I'd like to do right now is actually give you a little demo of PGShard and CitusDB. So if we could switch to my screen.
Переключите на лэптоп, пожалуйста.
That's my screen. So I've set up a little PGShard cluster with 3 worker nodes, 3 Postgres databases, and 1 master node, which has the PGShard extension. So I can here do a create extension PG shard. Oops. And I already did this before, so it already exists. So I'm using screen so I can switch between different nodes. So this is a worker node. Currently there's no tables on the worker node. I'm facing the one-handed typing problem as well. And this is actually a regular Postgres node. So I've set up a table here, customer reviews with 1 million rows. So on the master node, what I can do is I can go through the steps that I've already described to you. I'm going to create a table. So now I have a table, nothing special about this table. And now I'm going to distribute it. So I turn on echo so you can see which query is running. Well, this is the query we already saw on the slides. And the next query is the shard creation step. So that took slightly longer, and it took slightly longer because now if I look at the worker node, I actually have a bunch of tables. There's nothing in these tables. If I do a select count star, the latency is quite high from this table. Then there's nothing in it. All right. So my customer reviews tables is now managed by PG shard essentially. So what happens if I do an insert on it? So this just runs an insert, and if I look, I hope I got this right, it has landed in this particular shard. And so basically the data gets stored on the worker, and there will be another worker node which also has that data now because I set the replication factor to 2. So what I want to do now is actually make it slightly more interesting and actually insert a bunch of data. So this is going to insert 1 million rows into the PG shard table. In the meantime, I kind of wanted to look at the Postgres table just for comparison. So I have a query here, this one. So this gives me the 10 last reviews of a particular customer. Actually, this data is based or comes from Amazon. And so, you know, on Amazon, customers can review products. And so if you do that actively, you might want to see your last couple of reviews. So that's this query. And it takes about 170 milliseconds. So let me see if my inserts are done. Not yet. So let's run another query. All right, that's 162 milliseconds. And I'm just gonna wait for this. This is the drawback of giving a live demo. It's taking longer. Oh, I think it's already done. Right. Okay, so now I have about, actually I didn't run a count query here. So actually let's put in timing, sorry for the flashing, and count the number of rows that are in the distributed table using this query. And we'll see 1 million in one row because I did the extra inserts, but that should be okay. So this is not a great PG shard query. This takes 1.2 seconds because it needs to pull a lot of data from the workers. But actually, a really good PG shard query is the other one, the review date query. So this only takes 38 milliseconds on PG shard, where it took 170 on Postgres. And that's simply because PG shard has, in a way, much less work to do because it just has to scan one shard. I mean, I didn't create any indexes in Postgres. I could have, but I could have also created indexes in PG shard. Now, another thing I wanted to show you is actually CitusDB works with PG shard data as well. So if I use CitusDB to query my shards, I can do it even faster than Postgres, even if I do multi-shard queries. So that's most of the demo. So could we go back to the slides?
Переключите обратно на слайд.
Right. So that gives us some idea. PG shard is great for doing single shard queries, and you can scale this out to any number of nodes. Whereas Citus DB is great for doing multi-shard queries, so they go well together as well. But PG shard has some limitations. There's basically no transactions for doing multiple statements. So I mean, you can still do begin transaction and then insert, 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 end transaction. If one of them fails, the earlier ones will not be rolled back because they happened on the worker. There's also no transactions spanning multiple shards. There's no join support, but you can use Citus DB for that. By the way, Citus DB is kind of freely available for like small clusters. Just go to citusdata.com. And there's no unique constraints because the workers don't really know what kind of data is in the other shards. So that's kind of an inherent limitation to sharding. Now, we've just released PG shard, so this is kind of the first simplest version that we could come up with. And we'd love to hear feedback on like what would make you use PG shard. There's a lot of features that we've been discussing, like it would be nice if you could have multiple masters, so you could support very high insert rates, or make it easier to reshuffle shards when you add nodes. Like if you have feedback, please let me know or post it on GitHub or send us an email. So in summary, PG shard is a new sharding extension for creating distributed Postgres tables, which allows you to scale to very large data sets while keep maintaining very low query times for single shard queries. It helps you set up logical sharding, which will help you when you need to add new machines or when a machine fails. You could even just use PG shard to set up sharding and then handle a lot of the other logic yourself. And it's really simple to use. It's kind of transparent. You have a distributed table that you can just do an insert on. To use it, you basically just load the extension, create a table, and then distribute it, and then you can start running queries. And I mean, there's a lot of interesting potential use cases. If you think about the MongoDB use case where you have a scalable document store, we can now do that with Postgres as well with the new JSON-B data type, because PG shard works on Postgres 9.4. So you might be able to use that instead of NoSQL. And with Citus DB, you kind of have a data warehouse type solution where you can also do real-time inserts. So there's many possibilities, and we'd love to hear your feedback on it. And are there any questions? Sorry? How to change your tables, like do alter table command. So if you do an alter table command on the master, it will not change the tables on the workers. That will create an issue. But actually, the workers are just regular Postgres databases. So what we typically do is actually write a small script that would run alter table on all the shards and on the master, and then basically you've altered the table. It's a bit more involved, but if you have a script, it's just basically run the script. Is there a question over there? No, CStore is a completely separate extension. It might not be very useful in combination with PG shard because CStore doesn't have inserts. So it's like you bulk load data into it. So yeah, it's not immediately useful with PG shard. You could use it, but it doesn't do anything. But CStore is a completely separate open source project from Citus DB.
I suppose there was some limitation of using CStore and PG shard together without Citus DB. Perhaps I'm not right.
No, you can use CStore with PG shard, but like there's no restriction that requires you to use Citus DB.
Okay, thank you. And one more question: am I right that all the queries are going through the master node, and it can be a performance bottleneck? What should we do?
That is right. It's kind of currently up to your own creativity. You could set up multiple masters and, for example, just do the selects via multiple masters because they don't require locking. You could have multiple masters for different tables. I think at some point we'll add a feature where this kind of is taken care of, and you can connect to any PG shard node, and it'll keep consistency. Currently, inserts and updates are bottlenecked on the master.
But selects, I can route through the replicas of master node.
Sorry?
We have a master node, some physical replicas of it. Can I route select through the replica of master node?
Yes, if you set up a replica of the master node and install the PG shard extension, then selects will work in the same way, so PG shard will send it to the right worker node and give you back the results. So you can scale out selects in that sense.
Okay, thank you.
Еще вопросы, пожалуйста.
Is Citus DB a fork of any other database system, or it's completely independent?
Well, I mean, Citus DB is a fork of Postgres, but it's like a minimal fork in the sense that the changes we make to Postgres are very small. And so when there's a new release, we just reapply them. It takes us like a week to update to the new changes. So very soon we'll have one for 9.4. But it's completely built into using Postgres and Postgres abstractions.
Is it open source?
It is not open source. It is actually free to use for small clusters, so you can download it.
But free to use?
Yeah.
Thank you.
Еще вопросы?
So we've got a few questions over here. I'll repeat the questions.
How difficult it is to change the number of logical shards?
So the question is, how difficult is it to change the number of logical shards? Which is an excellent question because the answer is right now quite difficult. So the number of shards, as we've created it, are decided at the start. Now, so if you'd want to change that, you'd kind of have to pull out the data, create a new table, and put it back in, which is not ideal. But there are things we could do in that regard. So we could add functions that reshard or split all the shards. So that might be an interesting new feature.
Is it true that I can create really many logical shards, but use only few physical?
Yeah, like the choice of partition key is quite important. So the question is it true that I create like 100 shards, but because of the types of queries I'm making, I'm only using like 3 because I'm also always having the same customer ID, for example. And yeah, that is something you want to watch out for when you pick your partition key. It should be something that's reasonably well distributed in your workload. If it's customer ID and you have 3 customers that generate all your traffic plus a very long tail, then that's probably not a great partition key. So if I want to use these techniques as a data warehouse with many concurrent queries, concurrent users doing complex queries, what kind of problems or restrictions will I run into? So for example, if you use CitusDB as a data warehouse, the main restriction is that certain SQL features are not or not yet supported. Particular types of subqueries, like correlated subqueries, will not be supported. Some type of joins and window functions. We're gradually adding more SQL support, but I mean, you'll have to work with what there is. Other things like foreign keys are not easily supported in kind of a distributed table. And there's restrictions like that. And also particularly, you have to think about how am I going to shard, how am I going to partition my data? Because it's also not even just about, is this nicely distributed in my queries, Also, if you want to join tables, you might want to think about that in advance and basically partition the tables by the same key and try to ensure that the data that needs to be joined actually sits on the same node, because otherwise every join will cause a lot of network traffic, or actually the table has to be repartitioned while the query is running. So basically, if you join on something that is not the partition key, CitusDB would go through all of the data and make new shards essentially that partition it by that key. And so that's a pretty expensive operation that you want to avoid. So there's more kind of considerations that you have to put into how do I store my data, and also considering that some SQL functions that you might be used to will not be available, at least not right now. Got it.
So if I understood correctly, the master node is used for two things. One is storing the distribution relations, and in other words, state. And the other part is using for the Postgres, modified Postgres by extension to distribute the queries. Now, the first one needs store state, the second doesn't. So why not use, in order to achieve higher availability, use distributed storage for small data like Zookeeper or PGConf, and replace the storage of the distributed information by that, and then using the Postgres as a scalable system plus PGSharding you can have multiple masters then.
Right. So trying to phrase your question. So the master just stores a bit of metadata, basically, which doesn't change. And so why not kind of use, let's say, a distributed backend for that metadata? The main job, actually, the main reason there's a single master right now is not so much the metadata. The metadata is pretty static, but it's actually more in the locking. So when we want to ensure that there's only one update active at a shard at a time. And so currently the master is the one who has the exclusive, who keeps track of the exclusive locks for that shard. And if you have multiple masters, then there need to be a distributed locking solution, which we'd love to build, but we're still thinking about how to do it.
Again, I would say, why not Zookeeper itself?
Yeah, I think Zookeeper is quite suitable for these types of applications, so that might be a way to get there. We're also looking for like what's the simplest we could do. I mean, pretty much everything in PGShard right now is as simple as we could make it, and I think that really helps making it quite usable. But I mean, yeah, this is definitely something that we'll consider for like doing multiple masters. Zookeeper is an excellent solution to that. There's one all the way in the back there. What about bulk load? So there's various options. Again, it's kind of this is a thing that's up to your own creativity. We have someone using this right now who wanted to have copy where that's not directly supported by PGShard. But what we did is we set up a separate table that you could copy into with a trigger that would do an insert on the distributed table. That's a way to do it. It's not really bulk in the sense that everything goes through the master. If you want, you can go into the workers, do bulk loads into the existing shards. I mean, if you know this is all data for a particular customer ID, for example, you can just append it to an existing shard. So those are possible solutions.
Еще вопросы?
I've got one more. Yeah, you can use stored procedures. The only thing is you need to put them both on the workers and the master in advance, so there's a bit more overhead there. You will just not get maybe transactional semantics that you're used to if you're actually running a stored procedure on the master, because there's no rollback essentially of multiple statements.
Can it be possible to run stored procedure on the shards, which would use only the data of particular shard, or just
I guess
stored procedures on the master?
I guess the simplest way is to then set up the stored procedure on both the worker and the master and do like a query that hits a particular shard and uses the stored procedure.
Okay.
There's no way to directly connect to a worker and use a shard, let's say, from the master node.
Okay.
And then there's always the other, like, say, backdoor of, because the workers are Postgres databases, you can always go into a worker and run any SQL there.
Okay. And another question, if I redistribute the shards over the physical machines, which kind of lock does it use over the shard?
As of right now, there's no special lock that we've added. So,
But will the updates over those shards, which are now redistributed, will be possible or not?
so like if you want to, like, say, do rebalancing currently, that's
Yes.
kind of a maintenance thing, as in you at least need to, you could mark those shards as inactive while you do the rebalancing, for example, and then so no inserts can go into them.
Okay.
So that's a draw.
So I should stop all the activity, yes, when I do the rebalancing.
Right now, yes.
Okay.
So that's,
see.
again, something we might change in the future, but right now it's, you
Okay.
should stop.
Еще вопросы?
See, could you give him the microphone? Because
Sorry, I was asking about volatile functions. If you insert random or insert clock timestamp, and there's a factor of 2 of replication, will it detect and block it, or will it just write 2 different values?
I might not be familiar enough with Postgres to really be able to answer your question, because I'm not familiar with the term volatile functions.
So basically, what happens if you do insert into accounts random, where account ID equals 2, and it goes to 2 different shards? It's just gonna execute it on 2 shards separate independently.
I think in that case, like, we pick out those types of features and we say we don't support them right
Okay,
now.
yeah,
so that's
Okay, thank you.
So do you basically execute the same query on the shard, or do you calculate the row on the master and then insert it to the shard, already calculated row? I believe the
no, I
question
mean
was
the worker Postgres node handles the insert. So we basically send almost the same insert to each shard, and almost
okay, so
because
if
it's a
there is
different.
some function call in the insert, there would be same insert which contains a function call on the shard.
Yeah, so if, let's
Okay.
say, if that function would return a different value on both
Okay.
workers, you'd get 2 different values. Yeah.
Okay, so I believe that's the answer.
Yeah.
All right.
Yeah. Thank
Okay.
you.
Thanks.
Еще вопросы?
There's one over here.
Okay.
Our prepared statement. I think, no, PG shard doesn't support prepared statements right now. And it's because PG shard kind of replaces the whole query engine of Postgres. So we've thrown away all the SQL functionality basically, and then have to start from scratch. So those things are not yet included.
Да, Саймон, пожалуйста.
What are your plans for including this into Postgres core?
Well, we haven't drawn up those plans yet. I think there's still a lot of maturing that we can do to make this. Oh, sorry. Actually, the question was, what are your plans to include this into the Postgres core? And I think that right now, PG shard is at its most basic level. And I think there's a lot of maturing we can do to make this a really useful tool for, sharding and cluster managing a cluster with shards. So I mean, long term, that would be a very interesting. I think it would be a very interesting feature to add, but we haven't really given that consideration.
And will you be releasing it with the Postgres license?
I think currently it has an LGPL license. I'm not quite sure how we made our licensing decision, so I'll check with the owners.
Хорошо, еще вопросы?
There one.
Пожалуйста. Что? Да. Да.
Добрый день. Скажите, пожалуйста, а вы можете выполнять запросы параллельно на...
Can make parallel queries on node shard nodes, on all shard nodes.
You can execute queries in parallel on all nodes of the shards.
Yes. So basically, there's different levels of parallelism. Selects are by default parallel. So every time you open a new connection to the master, you essentially spawn a new process, and that can send queries to the workers in parallel. Any select will happen in parallel on the workers. If you do an update, there's only one update on a shard at a time, but you can still update multiple shards in parallel, basically. And so it helps having, let's say, at least as many shards as cores on your machine. So each core can be busy with like one update or insert.
Хорошо, был ответ на ваш вопрос? Ага. Второй вопрос.
Еще один вопрос. Вы упомянули, что вы используете...
That you are using join pool, and what is it? Is it an extension? If it is, then how is it implemented?
So you mentioned that you use connection pool. What kind of connection pool do you use?
Well, currently it's actually very simple. It's like a pool of size 1, where if there's still a connection open to the worker, the master process will reuse it. Of course, there can be multiple master processes, processing selects in parallel, so they'll each have their own pool of size 1, essentially. There's no like PG bouncer type pooling going on.
Okay, thank you.
Скажите, пожалуйста, а чем отличается ваше решение от PL Proxy, от Citus?
So the question is how your extension differs from PL Proxy of Citus.
So I know PL Proxy, and kind of what you do there is it's based on functions, basically. So you can't use arbitrary inserts, updates, and deletes. You can have a function in your, let's say, master node, and then also have it on the worker nodes, and then basically parallelize that. And you can actually implement a lot of functionality using that system, but it's much more involved and, less transparent. So you'd have to, PG shard, you could kind of drop into an existing application even, and it will work. And it's just quite easy to use, as in there's only really 2 steps that you need to take to make it work. So it's ease of use, I think, and kind of doing updates and deletes and replication and rebalancing are all useful functions that it also does.
Thank you. Спасибо. Еще вопросы?
Just one in the back there.
Да. Okay, the question is, there are two big tables, each of them are sharded. And if you run the query, which contains join between these 2 tables, where the join will be processed, on the shards or on the master?
So joins between distributed tables and regular tables are not supported. Joins between distributed tables, like two distributed tables, can
Okay.
be done using Citus DB, and that will be pushed down to the workers. And then it depends on like how the data is actually stored, where it is located. Sometimes we'll do kind of a local join where both, all the data that needs to be joined is on the same node. Sometimes we'll need to pull data from other nodes, and sometimes we'll actually need to repartition one of the distributed table. But a join between distributed tables is done by the workers, essentially.
Okay, how can I make sure that my join can be executed locally? So I need to be sure that they are sharded to the same physical machines.
So let's say you have a customers table and a customer reviews table,
Okay.
and you want to join those together. So the way it works in PGShard is if you create two tables with the same number of shards,
Okay.
and then they will basically, those shards will be located on the same machines. And because if you've partitioned both of them by customer ID, then like any join on customer ID will be performed locally.
Okay, thank you. Еще вопросы?
Okay, I have a question. If we have two logical shard of one table, for example, customer data 1 and customer data 2, you say that it selects from the first table. Is it always from the first table selects, or it can happen to the second table?
No, it happens randomly, basically, or it distributes.
So when we try to use join, it can be that query from different shards or not?
No, the replicas are all, like when you follow the same number of shards and same number of placements, the replicas are also placed on the same nodes because it's kind of a round-robin scheme.
Yeah, we have two similar logical shards, but can we query one table from one shard and second table from second shard?
I don't quite get the question, sorry.
As I understood, then the join will be performed on the master node if the involved shards are on the different machines. Окей. Так, я думаю, оставшуюся дискуссию можно
I believe that we can continue our discussion off the line. Let us thank our speaker.